So we're doing now the Bernstein-Vazirani algorithm. We're redoing it after many weeks after I did that first time. And as I did the Jossa the Deutsch algorithm, also based on just a Wikipedia article, I'm going to keep doing the same here. Let's see what happens. So the best algorithm which solves the Bernstein problem is a quantum algorithm invented by Ethan Bernstein. It's a restricted version of the Deutsch algorithm, where instead of distinguishing between two different classes of functions, it tries to learn a string encoded into a function. It was designed to prove oracle separation between, okay, whatever that means. The problem statement: given an oracle that implements some function, it is promised that the function is a dot product between x and a secret string s, which is, okay, so it's just a binary string, modulo 2. So you've got here f, so x times s modulo 2, which equals to this. Okay. Fine s. Okay. Okay, let's see. Classically, the most efficient method to find the secret string is by evaluating the function n times, because the circuit here I see is just apply Hadamard, then build a function, then apply the Hadamard again. So, but then apply Hadamard again. Okay, but so classically, the most efficient method to find the secret string by evaluating the function n times. Okay. Yeah, okay, because then you're finding each of the factors, because your input just has one. So one element flagged as 1 in here. So based on this definition here, in contrast to the classical solution, which needs at least n queries to the function, the quantum algorithm needs only one query, and it is as follows. So you apply a Hadamard transform to the n qubits. So that's what we see in here. Okay. Then perform a controlled negation of every state in the superposition generated by the previous Hadamard transformation, for which the oracle then, when applied to this state, returns 1. Okay. Another Hadamard transform is applied to each qubit, which makes it so for qubits where s equals 1 is the state converted from minus to 1. Okay. Perform a controlled negation of every state in the superposition generated by the previous Hadamard transformation, for which the oracle, when applied to this state, returns 1. But a controlled negation on what? Not so sure. Is it that, if I remember, Okay, does this mean that you're actually applying a oh, I don't get the oracle. So there's a code in circ here. And you've got the secret function. Okay. So, but I can take a look at this later. Initial qubits, append the oracle. Output, input qubits. And then append the oracle, and then measure in the X base. So apply a Hadamard and then measure. Okay, yeah. And the oracle, make oracle. Oracle. Main oracle equals make oracle input qubits, output qubits, secret factor beats. So the oracle, of course, knows where's the secret factor beats. Make oracle secret factor. So what it does is, okay, it's implementing the function blah blah blah. So okay, so it does do CNOTs. If secret bias beat, then no, the secret bias is I don't know if for qubit bit in zip of this, if bit, then control NOT of then control of qubit and output qubits. So it's basically controlled NOTs. But we perform a controlled negation of every state in the superposition generated by the previous Hadamard transformation, for which the oracle, when applied to this state, returns 1. So it's about this is because I feel like I'm left just to decide on how to implement that, and I wanted to know that, so just to understand the algorithm. But it seems that what you're simply doing is you're encoding, you're kind of encoding that as by just applying a control NOT. because it's not even like, so you apply a control knot for those inputs where it gives a 1. Is that what this is suggesting? Mm. Um, hmm. Kind of feel confused. If the secret factor is 1, then you apply control knot between the input and the output. So you've got output qubits, output only qubits as well. Input qubits, output qubits. Because this seems to indicate that what you're just doing is, so if you've got your input qubits in here, and then you've got like and then you've got your output qubits in here, right? And then you're only saying, so you're doing so there where the S is 1, you're just doing a control knot, right? Let's assume that this is this way. Yeah. And so what you're measuring then, so you're measuring the input qubits, not the output qubits, but you're going to have the S in the output qubits. No. Sorry, you do the Hadamard on. So you negate, so you negate the output qubits, then you apply Hadamard on the output qubits, on the output qubit, this one qubit, okay? And then so the circuit is using an output qubit, and then you're doing a Hadamard on each of the input qubits, and you're measuring the input qubits. This output qubit, I would say it seems to be an ancilla one, and then but then the oracle, and what is the oracle doing? It's a control knot. If the secret factor is 1, then you're doing a control knot. So let me clean that up. So what this is saying is you've got your let's say input qubits, and then you've got one output qubit, and so if let's say the string is like just all ones, right? So and here starts the and so this is initiated at 1, and then there's a Hadamard here applied. Uh, uh, then there's a Hadamard here applied. Mm. And then you're basically applying the control knots here. Yeah, and here you've also got a bunch of Hadamards here applied to all of these. And then you actually apply a Hadamard here as well, and a Hadamard everywhere, but you're only measuring, so you're only measuring, and then you kind of measure only these ones. And that's how you implement the function, yeah? Because, yeah, I mean, mm, 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 mm. Hmm. You play Hadamard. No, you're not applying a Hadamard at the end there. It seems like. Then what the heck is this in here? Output qubit. You're not applying that. You're not applying Hadamard here. So is that the right? I probably should go and check out the and some other circuits to make sure that I'm not just losing my time here. But um, so basically, you're not measuring that. Each input qubit, and then measure the input qubits, and that's it. That's what it says here. There's no Hadamard on the output qubit. Nevertheless, the control knot is on the output qubit, on the Ancilla qubit. Seems like a similar technique done with a Deutsch user here, kind of thing. But like, so what is it really doing? You've got like, so you've got your again like two. You're kind of duplicating your input space, but here's all minuses, right? Uh, and then you're doing control knots on this guy. How does this affect any? How does this affect any? Mm-hmm. Trying to think if this is a. Mm, mm, mm. Hmm. Let's say you've got. Hmm. Mm, mm, mm. Hmm. Trying to find a way to sort of intuitively. Hmm. Mm, 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 mm. So if I to the 0, why would this? I'm not sure. I'm not sure this is the right. I'm not sure this is the right circuit. I'm not sure. Maybe that's not the right. Let me just quickly double check on another tab, which you won't see. So, Einstein. I'll put it right now. Just trying to find. I'm just trying to find. Maybe I'll just copy paste my search. I'm just trying to find an actual circuit or something. Mm. So input, output. Yeah, so they're also using sort of an ancilla qubit. Yeah, so that's what I was basically painting, right? Oh, phase kickback. But that was supposed to happen with control Z. Oh, well, yeah, that's a control Z. That in here is a control Z. Yeah. Yeah, okay, so I was kind of getting it right. Okay. So I'm happy because it means that I write that correctly here. So, but intuitively, I'm gonna try to have that. How can if this is something that I can kind of, I'm not. I don't know. Maybe I'm tired. Uh, it's a bit late. But so basically, you've got your qubits in here, and then the ancilla qubit in here, and so and uh, don't like to think of it in terms of phase kickback because because mm, of it in terms of phase kickback. Mm, I mean, yeah. Why not? I don't know. Maybe it's not my day. It's just like, yeah. If there's a Hadamard in here, if there's a Hadamard in here, and there are Hadamards all over the place in here. Uh, hmm. Then you're, I don't know, not happy. I mean, yeah, you could ignore the Hadamard and then talk about a control set and then say you're doing. You then say you're doing like like a controlled Z, right? Like these control Zs, and so you're turning each of those, which are, sorry, not here, but like after the Hadamard, they are each of these qubits in the plus state. So and then that puts them into the minus. So when you apply a Hadamard again to all of these, then of course minuses will go to 1 and pluses will go to 0. So that's how you read that kind of secret string. But it's, I don't know, this is just so I thought it would be fun to revisit these algorithms, but it's like uh, at some point you're like, what's the relevance of these? Yeah, it just serves to, of course, showcase some of these things, some of these quantum features, but it's not really maybe worth spending more of the time. But it's like I was trying to maybe explain it in terms of sort of the Hadamard, sort of the non-phase, the non-phase kickback explanation. So you've got the Hadamards here, and then you're doing control knots. I think it's just hard to explain this way because terms of interference, because in terms of interference, you've got the 0 and you've got the -1, and then you've got all the other different possibilities. So you're kind of duplicating your inputs. Like I'm trying to use the same similar explain it like I did with when I visited Deutsch's algorithm, but yeah, and then you're like, yeah, control knots. So just for those states where, just for those inputs where the function outputs are 1, you actually apply a control knot. Not which kind of means you're flipping. I don't know. It's not my day. In terms of phase kickback, yeah. I feel like I shouldn't be spending more time on this, but if I don't, then I feel bad about it. I'm just finding another, is it a neat way to explain what's happening here? When we kind of say, okay, when we apply the control knots here, for example, right? And then the Hanamarts. Then you're just measuring these guys. In terms of constructive and destructive interference. That's what I'm also kind of trying to because for those cases where so I'm basically applying a control knot. Only where there is a 1 in the hidden S string. Yeah. That's what you're doing. This is really weirdly written in here. Control negation. Because it's not a control negation of every state in the position generated by the press. So which were applied the return returns 1. So apply a control knot. Okay. And see what you end up measuring is that it's particularly that action that the S string is kind of having, right? Yeah, I don't know. It just doesn't make. It's not my day. It doesn't make any sense. It's just It's just to showcase in this case to showcase the phase kickback. This is not happening here. Doesn't need to happen here. Oh, does it? It does. Yeah, it does need to happen. Whatever. No. It's so let's just make an example. So if we've got 0 0 0 1 1 0 1 1 and then our ancilla qubit is this one here, and then you're gonna basically have these, right? If the secret string is 1 1, if the secret string is 1 1, right, then and then you're gonna have the, then what you're gonna have is so here you're gonna have here you're gonna have a 1, and here you're gonna have minus 0. Then here you're gonna have a 1, and here you're gonna have a minus 0. And then you're gonna have a 1, and here you're gonna have a minus 0. And so if you now want to make Hadamard's of all this stuff again, you've got I think if this is a good way to reason this, because here there's no there's no neat way to explain that. I mean, I can't find a neat way to explain that. And now if I would like to apply the Hadamard's, hmm. 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 Don't know. Don't really know. 111. Hmm. 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 Yeah, I don't know. I really don't know. I'm not thinking from that point. I'm not thinking, so I'll just, yeah, I feel I'm totally lost because if I would now group things to look in the Hanamarts, where where is this? Where is this taking me? The trying to explain it in terms of interference and stuff, and it does not. It just doesn't come. It's not. It's not like I don't know. Mm, mm, if I would group these, no, these, and these, then what? Hmm. 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 In terms of interference, I mean, yeah, you can probably explain everything in terms of interference, but it just becomes cumbersome to explain that because what you're doing is you're doing control knots. You're doing control knots. Mm, hmm. I mean, basically, you're putting in the plus state, and then the control knot flips it into the minus state. Because you've got a plus state and you've got a minus state, which is your ancilla Q is in the minus state. And so when you do a control knot, uh, so you've got uh, Mm. Because literally you've got something. This is going nowhere. I gotta think about it differently. I don't know. I don't know if it's worth it. This has been so far a waste of time to try to explain this in a different way. Yeah. Mm. Mhm. Mm. I'm gonna title this video 1 hour in silence. 0 minus 1, and 0 plus 1. Yeah. I mean, if you've got like 1, 0, and then you apply a Hadamard to both, then you kind of got like, let's first apply it to, so you've got 1, 0 plus 1, 1, and then the next step is you apply now to the first qubit, so it's 0, 0 minus 1, 0, and 0, 1 minus 1, 1. That's what you have. That thing is this. And then if you apply control knot like this, yeah, so you basically you basically end up with 0, 0 minus 1, 0 plus 1, 1 minus 0, 1. And so what you've done is probably turn it into, probably that's what you've done, right? Because what no, sorry, correct. Because if you've got 1, 1 and you apply Hadamard to both, then you have 1, 0 minus 1, 1, and then now you apply again Hadamard to the first one, so you've got basically 0, 0 minus 1, 0, and then 0, and then you've got minus 0, 1, yeah, plus 1, 1, and this is the same as this one, which is basically what's happening here. So, but this is uh yeah. that's basically uh, that's what's happening in terms of constructive and destructive interference. Is nothing else uh, than you're tinkering with. Give me a second, because so basically, I mean, just whatever. Don't watch this video. This is just me getting lost into something that's totally unnecessary, which is nothing really. I just kind of recap the algorithm. Cool. Read a bit of a Circ program. I understood it. Good. Yeah, I mean, it's just it's like the whole thing with interference, constructive and destructive. It's attractive, but it just at some point you have to get a bit away from it because it's really low level, right? I mean, it's what's happening here is you've got one kind of qubit that this one here, the ancilla one, that you initialize with one, and so when you apply Hadamard gate, you're creating a superposition that is that has a different phase, relative phase than the other ones. So and that's where the control knot kind of when you use the control knot to basically selectively change the 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 phase to the ones where you want to change this relative phase as well. So when you apply it harmonics again, then you kind of read ones instead of zeros, and that's all what you do. It's just yeah, I don't know. That video was totally unnecessary. I don't know.